So a very warm welcome again to everybody on this third edition of the SIP of Science initiative. That is the product, it's a joint work of the Department of Anesthesiology Intensive Therapy and the Center for Translational Medicine at Semmelweis University in Budapest. And we have a great pleasure today to have Professor Rob Robergs with us. And it's an interesting story. We just recently met on a conference called Colors of Sepsis in Ostrava, which is the biggest sepsis conference here in Central Eastern Europe, with more than 2,000 delegates. So that's quite a massive event where on the hot topic section, both Rob and myself were keynote lecturers. And I must say that it doesn't happen very often, but I was really dumbfounded by his presentation. And and we have been in contact ever since. And when I approached him with this request, whether he would be willing to give us a lecture, despite the time difference between Australia and Europe, he was immediately agreeing. In fact, he offered that he will go into his office in that very unsociable hour to have a better internet connection to give you an even higher quality lecture. But now he's at home. He's with us. That is most important. And Rob, we are really looking forward to this really paradigm shift, change causing lecture. So over to you.
Yes, thank you very much. Pleasure to be here. This lecture kind of takes you on a bit of a journey of my career over the last 30 years. So it's really geared to providing you a lot of background information about understanding fundamental chemistry, which you all have some training in, obviously, to be where you are, and it identifies the reasons why I had questions and presents the evidence for that, and that will be the bulk of the talk, really. And I start off on the title slide because history is really important here. When I tried to elucidate answers to all the questions I had as both a student during my PhD and in my initial years after graduating, it really all came down to really understanding the role of history in how we think and do some things the way we do, no matter what our application of the science that we're involved in. And to start off with, if we just talk about lactic acid, it's really important to understand that research and knowledge about lactic acid was occurring as early as the late 18th century. And it became a molecule that gained a mystique, far beyond its relevance, really, early on. And so in terms of isolating its structure, identifying its crystal structure, its purification, all these things occurred well before we understood anything about acids and bases and the pH dependence of molecules that we label as acids or bases, and more on that in some future slides. And, we didn't even know how acids function chemically until, the late 18th century. And then it wasn't until like the 1920s that we had an accepted definition, or the erroneous definition of how chemically an acid functions in an aqueous environment. So more about that a bit later. But that's very, very telling, and it sets up a very much long period of time where lactic acid just entered into our scientific vernacular. But the real crucial issue for you more than me, I mean, I'm not a doctor. I just try and solve problems that I identify as a physiologist and metabolic biochemist. But I'm just in total admiration for how you have to work. You've got a patient, multiple organs are failing. How do you treat them? There's a severe acidosis. What's going on? What do you treat first? Things that you have to work out because there's not a lot of research for all those specific patient conditions that confront you. And I guess that's where we're going to end the talk with, what does what I present to you mean about how you practice by the bedside. So the talk structure, we'll go back to just some traditional concepts about what you and I have always been taught when we studied to be where we are, and why then, as I progress through the talk, that is potentially wrong. So we'll identify problems with that. We'll look at the biochemistry and just apply fundamental principles of organic chemistry and biochemistry and see what that tells us. And then look at some added evidence, and then look at what I've done to try and present a different picture of how we understand the development of at least the metabolic side of a systemic acidosis. And as I mentioned, we'll try and finish with some presentation from my side, then hopefully some questions about what that means to your clinical practice. So we've covered the history, really quite important. My work first began when I identified in my lifetime, I found this research during my PhD, so it would have been the late 1980s. And the first critical evidence against lactic acidosis that I could find actually was published in 1977 by a cardiologist called Givers. And then about 4 or 5 other really critical commentary manuscripts were published and recognized that, wow, this lactic acid concept has quite a few flaws in it. But that work was mostly ignored. And then I came along in 2004, I published a manuscript in the American Journal of Physiology. And that was kind of instrumental in my field, which is kind of like applied and integrated physiology, for changing the way a lot of us have understood acidosis. And that led to more work based on some constructive criticism I had from some content in that manuscript. But let's go back to the basics. We now know, based upon the Arrhenius definition of an acid, which again was established, like I mentioned, in about the 1920s. So an acid is a molecule that can release a hydrogen ion in an aqueous solution, and it's somewhat pH dependent. So really, an acid does that. It releases the hydrogen ion at pH values 7 or below. And the Arrhenius definition results then in an acid that releases the hydrogen ion, and then it becomes a base, or what we might call an acid salt. But even in this diagram that I just grabbed from Google, they presented the involvement of water wrong. So we don't have the final products being hydrogen gas and a free radical oxygen. We really have either what we call the hydronium ion, which we generally regard as just free hydrogen ions, but there's a good argument that it's really the hydronium ion, H3O. There's water, and then there's hydroxyl molecules. So that's what's left from that simple little depiction of what an acid is. And there's a really great manuscript based on the history of what we know about acids by Lesney. And so I really recommend having a look at that, because it really reveals the controversy and the confusion about, wow, how do we understand acids from a chemical perspective? So really quite revealing. Yeah, when you look today at how clinically metabolic acidosis is viewed, and you can go straight to the National Kidney Foundation, in terms of the US, and it's very much based on the concept that cells produce metabolic acids, and they leak out or transport out into the blood, and then that changes blood pH, and there you have it. That's what we call metabolic acidosis. So when you focus on lactate or lactic acid, we call it a lactic acidosis. And that led to things like our understanding of acid-base balance, such as the standard base excess, the anion gap, and understanding the role of the partial pressure of CO2 in driving added hydrogen ion release in blood, and therefore the role of bicarbonate, both from a metabolic perspective as well as a renal function perspective, and also then blood proteins in pretty much establishing the role then and the end result for blood pH. In my field, in exercise physiology, we went even further, and we said, well, let's just assume lactic acid is our sole hydrogen ion provider. And that means then if you look at the change in lactate over the change in pH, you've got a measure of buffering capacity. So in exercise physiology for skeletal muscle, we use the unit likes for many, many, many decades. So, but my early awakenings came because I I mean, I don't know how to explain it. I really enjoyed my study of biochemistry, and I studied organic chemistry as a prereq development prior to my movement to the US from Australia to better prepare me for what I knew needed to be a more basic science foundation to my understanding. And when you look at, for example, phase 2 of glycolysis, we know that for the structures of the products, so these structures on the right represent the main products, right, of the reaction that they're connected to. So our first carboxylic acid, so a molecule that ends with a C double bond O and then a ion oxygen or a charged oxygen atom, and that's its base or ionic form. And when there's a hydrogen ion, right, integrated or associated with the charged oxygen atom, that's its acidic form. But when you look at any modern biochemistry textbook, they're all documenting metabolites that are carboxylic acids, labeled as an acid, just by nomenclature, right? Because of this carboxylic acid functional group, the C double bond O oxygen, they're formed in their ionic or base form. So you could argue quite clearly that there really is no cellular metabolic acid production in biological systems, and we know a lot now about hydrogen ion transport and hydrogen ion exchange proteins, and they're very much involved in the regulation of hydrogen ion balance, and essentially, as I will argue, the development of an acidosis. And you progress down. So once you produce like 3-phosphoglycerate in a cell, that's then that carboxylic acid functional group remains the way it is. You'll go to 2-phosphoglycerate, right? Then you get phosphorenol pyruvate, and then you get pyruvate. And it's all then about understanding, well, if we're not producing metabolic acids, then how do we get acidic? And that was the observation I had probably around 1996. And so I went straight to my chemistry department at the University of New Mexico, and I said, what's going on here? I've been taught this. And many of those chemists said, well, we've known for a long time there can't be metabolic acids produced in cells. But of course, they weren't interested in acid-base chemistry or physiology. They were interested in other things. And so I had to try and sort this out on my own. Now, when you look at the reaction that sometimes probably keeps us up too much at night, it's really quite straightforward. You've got the reduction of pyruvate, so lactate, and NADH provides a hydrogen ion and an electron. But you need another, and actually 2 electrons, and you need another hydrogen ion to end up forming lactate. So when you look at the chemistry, when a cell produces lactate, it actually consumes a hydrogen ion. So you would call that a metabolic hydrogen ion buffer. So lactate production in a cell, right, based upon this chemistry, is a means to help control or restrain the development of an acidosis. So that casts a whole new picture on how we view lactate. And in that case, then lactate with a negative charge, if you infuse lactate into somebody, it's going to pH dependent acquire a hydrogen ion for a small proportion of those lactate molecules, and then help buffer, right, the acid-base condition you're dealing with, and so help then raise pH. And then you might say, well, Rob, then it's forming lactic acid, which it is, but it's not going to release a hydrogen ion because of its pH dependency that it actually gained a hydrogen ion, and that came from water, the aqueous environment of whatever fluid system you're looking at. And even though it might be only 0.001% of all the lactate molecules that do that, if you understand Avogadro's constant, right, 6.023 times 10 to the 23, that's the number of atoms in a mole. And if you talk about the millimolar range, so 6.023 times 10 to the negative 20, or sorry, 10 to the 20, you don't need, a small fraction of all those molecules is still a large number of molecules. So free lactate or the lactate ion, right, infused in somebody will just based on chemical principles, right, raise pH. But then when you read some biochemistry textbooks, you see, even though they present molecules produced from metabolism in their ionic form, they then say that, exactly this about lactate when it's produced, right? It then somehow is lactic acid, and then that's the cause of the acidosis. And in this case, it's done it in the context of contracting skeletal muscle during more intense exercise. And then, of course, around the 1980s, late 1980s, Peter Stewart came out and provided a very different option for us to understand, which is the physicochemical model, where he argued that, especially for blood, that the pH of blood is regulated by balancing out charge. And when there's an imbalance in charge between two different systems, you're going to get a change in strong ions, and that change in strong ions is very much then going to drive hydrogen ion release in water from the hydronium ion to free protons, or from water itself to more hydronium ions, and that will lower pH. And then core to that, though, to Peter's theory, was that the hydrogen ion exchange from chemical reactions has nothing to do with changes in pH. So that was a pretty constraining assumption based upon what we've already looked at. And I'll show you evidence for why that's concerning here pretty soon. All right, so what I did very early on, I said to myself, gosh, Rob, if you're going to try and challenge a construct, you better make sure that your understanding of this is right, and the organic chemistry is doing what it tells you you think it's doing from the depiction of chemical reactions. And so I did. So I went into my biochem lab, and I just generated a biological solution in a test tube, and I looked at key reactions of glycolysis. And I wanted to know whether a chemical reaction does directly change the pH of the solution. And so I just prepared a supported environment, right, in a beaker to run, in this case, the lactate dehydrogenase reaction. And when you look at it from a structural presentation, because based upon the organic chemistry and the biochemistry, it's actually using a hydrogen ion from solution, right? You would hypothesize then that, wow, this then must directly change pH, and it must raise pH, right? And of course, that would oppose Peter Stewart's assumption in the physicochemical model. And so I ran this, and so I was recording, right, pH, right, during the progression of a chemical reaction in a beaker. And yeah, lo and behold, right, it does everything that the organic chemistry says it does. So there's an increase in pH, and in this case, quite dramatic, but the profile isn't all that relevant because it's just going to depend on the kinetics of the reaction and the changing substrates and products. But the profound result is that, wow, a chemical reaction, a balanced chemical reaction, right, does have the ability to change pH, and it has nothing at all to do with whether or not, right, it's producing a metabolic acid, because in this case, lactate, based upon the traditional theory, is an acid. It's just the resultant form after it's dissociated to lactate and a hydrogen ion, but certainly not, right? We have the increase in pH, and lactate is produced as lactate, and the raising pH is caused by the involvement of the hydrogen ion as a substrate. And then if you look at the ATPase reaction, and this was the argument from Giebers back in 1977, whenever you break down ATP, you're going to release a hydrogen ion because it involves water. So this actual reaction is not quite presented right in the written form, but when you add the water molecule to the understanding and balance out the chemical reaction, certainly then you see how water hydrolysis ends up releasing a free hydrogen ion, and lo and behold, right, when you run that as a system, you get what the organic chemistry says you get a decrease in pH. When you do that for another reaction, it's another oxidation reduction reaction like the lactate dehydrogenase reaction. It's a glyceraldehyde 3-phosphate dehydrogenase reaction. And prior to my work, this hasn't even been on the radar of a reaction that should alter the pH of an aqueous solution, but being a reaction that involves oxidation reduction and also further involves inorganic phosphate as a substrate, which has the ability to actually buffer hydrogen ions as pH drops below 7 inside a cell, and then becomes dihydrogen phosphate. So it has another hydrogen ion connected to one of these oxygen atoms. And that means there's now more than one hydrogen ion to release when it's involved in this reaction in the phosphate addition to glyceraldehyde 3-phosphate, forming 1,3-bisphosphate glycerate. And so this hydrogen ion release can be more than one, and I'll show you the evidence for that a bit later. And there you go. So pH goes down. So I haven't published this work yet because at that time I was doing this for myself, and I had no time to do it properly for what would be the required quality for publication. But this is what I'm going to do when I visit the Czech Republic later this year. I'll be doing this in great detail. I'll be looking at glycolysis. I'll be looking at ketogenesis and ketolysis as well, and also the pentose phosphate pathway to just show what these reactions are doing with regard to hydrogen ion exchange. So there's the evidence for having us think very, very differently about the source of these hydrogen ions during the development of a metabolic acidosis. I mean, we know, and you have to deal with added causes of acidosis. You've got to deal with kidney function, and it's perhaps dysregulation and altered function during the conditions such as sepsis, for example. But this just depicts what goes on in a biological system. So chemical reactions, regardless of whether there's a acid metabolite produced, can change the hydrogen ion exchange of a system. And so I then went on to try and compute what's going on. So I modeled my work off Kushmerik's this multiple equilibrium of cations and metabolites and how it relates to bioenergetics. And I published that work in PLOS One in 2017. To get this done, I had to replace a simultaneous equation that Kushmerik never really revealed. And I went to an organic chemist or a computational chemist, and he said, "Oh, Rob, you need to use this equation. It's called an alpha equation, and that's this large one right here." And you'll see how I did that. So then what I did was I worked out, first of all, in Excel. All right, so I'll follow a pH range from 6 to 7 because for my world, skeletal muscle, its pH can range from 6 to 7 depending upon the exercise intensity and the type of muscle it is, like slow versus fast, for example. And what's highlighted here is cell C23, right? And there's the alpha equation based upon the dissociation constants that I knew about for the hydrogen lactate versus magnesium lactate. And then you can work out free lactate, bound lactate, and then know what the pH dependent expression is relative to whether or not there's hydrogen ion association with the molecule of interest. Now, if you do that for all the molecules of a metabolic system that you're interested in, you can then look at chemical reactions. And if you know what the hydrogen ion status is for a given pH, for a given metabolite, you then can work out what a chemical reaction pH-dependent hydrogen ion coefficient is. And so that's what I did in that 2017 manuscript, and essentially presented all that data for the metabolites of the phosphagen system and glycolysis, and of course for the ATPase reaction. And I do all that. I do my own programming. So I've been programming since the early 2000s, and I use LabVIEW. So it enables me to ask questions and answer them in a really unique and original way. And from that, I could then identify, I could look at each chemical reaction. And here again, from glycolysis, you can then reveal what a chemical reaction is doing in the context of hydrogen ion exchange in terms of release or uptake. And anything negative is release, and anything positive is uptake. And obviously you can see the PFK reaction and the hexokinase reaction of glycolysis are very hydrogen ion releasing, and most of the others of phase 1 are of minor relevance. If you look at phase 2, so the ATP regenerating phase of glycolysis, right, it's really the glyceraldehyde 3-phosphate dehydrogenase reaction that is profoundly hydrogen ion releasing, but so too is phosphoglycerol-kinase, to a small extent enolase, and the others, and especially lactate dehydrogenase, are very hydrogen ion consuming, and lactate production has a hydrogen ion coefficient that's really stable and close to 1, right, across the biological pH range, at least for a cell. And of course, for that in blood, you would need to go a bit higher than 7, of course. And then then I modeled more intense exercise, like a 3-minute bout of intense exercise, and used as much of prior research data and metabolite accumulation as I could. And so this ignores the function of the mitochondria. So it just looks at glycolysis. And then you understand where the hydrogen ions come from in the development of that acidosis, at least for skeletal muscle. All right, so where to from there? Well, I've done work on, right, hepatic ketoacidosis, and we've just published this last year. So I kind of collaborate. Well, Sam was one of my PhD students, but I collaborate with 2 other physicians, Marek Nalis, and intensive care physician, and Steve Curry runs a toxicology department in Phoenix, right? So Banner University, and he has for a long time. He just sourced me out and wanted to learn more about acidosis for his line of work, which obviously relates to poisoning. And so, of course, our hypothesis would be, based upon what we've done, that, well, acetoacetate and beta-hydroxybutyrate are not produced as metabolic acids, and the hydrogen ion release from ketoacidosis must come from another source. And sure enough, when you look at ketogenesis, the most hydrogen ion releasing reaction, or really the only one, is the production of HMG-CoA. The production of beta-hydroxybutyrate actually consumes a hydrogen ion, and when you convert acetoacetate to acetone, you actually also are consuming a hydrogen ion. So it places the context of the acidosis of ketosis into a different mindset, and it's not really, as best as we can tell at this time, totally relevant to blame the production of ketone bodies for the acidosis. There are other coexisting conditions metabolically that must be providing the hydrogen ion release, and one of them is, right, in ketolysis, when you actually convert beta-hydroxybutyrate to acetoacetate, you're actually having profound hydrogen ion release. So we published that last year. The information to look at is really in the table on the right around the hydrogen ion coefficients, and you really see then that in the production of HMG-CoA, right, you've got your main negative coefficient, and all the others are positive, and on the ketolysis side, you see what I just told you. So again, it's not very clear, right? So where do the hydrogen ions come from? More work still needs to be done on better understanding, right, ketoacidosis. Now, my students always ask me, well, they say, Rob, well, how can this be true? Why has such an error been made? And I find I have to talk about this, and I don't want to spend too much time on it because I want to save time for questions about what all this means to your clinical practice. But my study and reading of scientific philosophy led me to understand that, well, there are always errors in science, and it happens all the time. And if you read Karl Popper's work, he talks a lot about our prior education, is somewhat inclusive of some errors, and unless we are wise and think more clearly, we can be distracted and misled by some of what we've been taught in the past. And then if you that way, you can't see the anomalies or the data that opposes the historically accepted theory. If you can't see those anomalies, right, you can't find your right solution. And that's my argument in my field, in exercise physiology and more integrative physiology. And I would assume it's also true in medicine. And of course, when you read Kuhn's book, right, and although Kuhn's been oftentimes criticized for not being so as critical as he should have been about his own work and his own understandings, but he defined this normal science concept quite critically. And it presents a situation where there's a whole force in science that is not intentional, but just natural, that relucts change. And once something's been established, it's really hard to change it, basically, is what history shows across numerous disciplines and topics in science. And, Popper has always said that it's just unfortunate, and we have to do our best to change that. Hence why I do what I try and do with my research and writing. But it's really important to do this extraordinary science because in identifying these anomalies, it's a way to craft a new way of looking at things. And instead of being stuck in an outdated paradigm, we are somewhat revitalized and move on and learn more things and hopefully help humanity in that more enlightened state. And that's the process. And it's just a shame that the time axis is in decades, right, not years. And so what does that mean for your conditions you're working with? Well, it depends on what you're looking at. I mean, in sepsis, it could be an inflammation. It could be mild poisoning. It could be anything that deals with an altered view of whatever metabolic pathways are consuming hydrogen ions. And in this diagram, I just focus a lot on mitochondria being a major hydrogen ion consumer. So if we're doing anything, or if a person has whatever condition that confronts or deteriorates the function of mitochondria, there's going to be a consequence to acid-base balance at the cellular level, and then, of course, at the blood level. And so, what do you treat? Well, as we'll talk about very, very soon, right, we know that we can, as I mentioned earlier, we can somewhat control blood pH. And if the acidosis is actually worsening the condition of your patient, there's a way to do that based upon everything that I've just talked about. And I know that some intensive care physicians, and this was discussed in Ostrava, actually infuse lactate and as a means to start raising blood pH, and then you can deal with the more mechanistic cause of the problem without worrying about the acidosis. But that's you're all better trained than I am to elucidate how you can use this information. Like I mentioned before, I'm not a physician, but I think the data is pretty obvious. We need to start thinking about acidosis in a different context, and the involvement or the generation of acidosis is more complex. It involves more chemical reactions, and we can't just blame one molecule anymore for a systemic metabolic acidosis. It's more involved in that. But lactate is still a good marker for a change in metabolism. And when blood lactates go up, that there's an increased dependence on glycolysis. And as I've shown you, that means there's a more complex activity of hydrogen ion exchange with a net release that can contribute to the overall systemic acidosis. So that's pretty much what I wanted to share with you today. It's pretty focal and to the point, and I'm wide open for any questions and discussion.
Thank you very much, Rob. Well, that most of us here in the studio, and of course in front of the screen at home, we are clinicians, mainly intensivists. So quite large part of your talk was completely in an unknown language, But I wonder if there are any questions. No questions in the chat Q&A yet, and I'm not surprised, by the way. But I mean, I have a few comments and questions because this is a very frequent, not a very frequent, but not a rare finding in our profession. The dogmas are carried on, and we are taught with dogmas, and they don't want to change, right? And this is also true for lactic acidosis, which was a paradigm that nobody really doubted, and we've brought up generations in that, and it had a serious effect, by the way. And one was that, for example, in diabetic ketoacidosis, the guidelines, the treatment guidelines, regardless whether they were released in Europe or the United States, they suggested so-called normal saline for resuscitation, which has a chloride of 154 millimole per liter. And many of my colleagues were afraid to give lactated ringer because of the lactate. And they believed that lactate will make acidosis worse, which is, listening to your talk, is completely the opposite. I was not aware that lactate is basically a proton donor, so you can make acidosis better by infusing lactate. Is this statement correct?
Yeah, a proton receiver.
Yeah, but
Yeah,
if you
receiver.
Yeah, if you infuse isotonic 0.9% saline to your patient who has severe metabolic acidosis, you can make it worse.
Yeah, yeah, that would be true. Yeah.
So, you know, this is a dogma that is published in guidelines, and we are just about to publish a meta-analysis on this topic, by the way, and hopefully it's it went through the first revision. It's on the editor's desk, so anytime. So we hope to get into the guideline with this, and your philosophy and your it's not philosophy, basically it's proven what you showed us here, that we are totally on the wrong track. Nevertheless, we can still use lactate, as you said, as an indirect indicator of metabolic acidosis.
Yeah, yeah. As a high probability that it's occurring. Yes.
Yeah.
Yeah.
And can you just elaborate a little bit more on that glycolysis story? Because to my understanding, when oxygen demand is met by oxygen delivery, then the citric acid cycle kicks in, and no extra hydrogen ion is produced. But when oxygen demand is greater than what is delivered, in your research, it is excessive muscle work. In our practice, it is critical illness or shock, basically. Then the energy is not produced, the ATP is not metabolized within the mitochondria, but in the extra mitochondrial carbohydrate resources. Is that correct?
Yeah, that's right. Yeah.
And this is the problem.
Yeah, yeah. So that's where glycolysis kicks in, and that's where these reactions all come into play, and you've got more PFK reaction occurring, and for glucose entry, I mean, if you're talking about the liver, but you've got the hexokinase reaction, and so then glycolysis, you know, becomes very much proton releasing, and if the mitochondria can't handle it, those hydrogen ions have to go somewhere else, which is the blood. Yeah.
If you go to your next to last slide, with the mitochondria, I mean, even here, go back one slide, please. Here. So that means that the release of glyceraldehyde, 3-phosphate, blah, 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 and ATPs, that is the key for metabolic acidosis when oxygen demand is not met by oxygen delivery. Is that correct?
Yeah, I'd say they're the largest contributors of the proton load, yes, of that metabolic condition. Yep.
Yeah, and if you go to your next to last slide, with, you know, this cartoon where the mitochondria, this is it. So I think that is the one we should remember for when work is increased, then glycolysis kicks in. That's correct?
Yes, yes. Yep.
So that's just for the audience who saw this lecture for the first time.
Yeah, and for yeah, and so there's your large source of hydrogen ion release. Yeah, and so I'm proposing that's majorly contributing to the development of the acidosis, not a lactate only scenario.
Yeah.
Yes.
Okay. Well, any questions from the audience here? No, these are all resident doctors here. So, you know, they should remember better for biochemistry than I do. So, Rob, anyway, thanks very much, and a big congratulations for your real groundbreaking work, and keep up the good work. And I hope to see you here in Hungary live, possibly next year on the SEPS East conference.
Yes, love to. Yeah, love to be
Okay.
there.
Well, thanks very much. Go and have a good sleep now.
Yes,
You
thank
well
you.
deserve it. Okay. Thanks a lot. Bye bye.
Bye. Bye.
And the same bye-bye to the audience. Thanks very much for joining in. And see you in 1 month's time, because in 2 weeks' time, it's the SMART conference in Milano. So everybody who would have been invited, I keep the English because there are attendees from abroad. So no sip of science in 2 weeks, because the traveling circus of experts are in Milano at that time, and we will meet in 1 month. So we will keep you informed. Bye-bye.